So hello, today we're going to start chapter 23, which is the beginning of magnetism. We've been talking about circuits and resistors and voltage and current. And now, yeah, we're just like, okay, enough of that noise. Let's jump all the way to magnetism. It seems kind of out of left field, admittedly. Um, and there's a lot of electricity we haven't covered yet. I said we're going to do AC and DC, but now we're doing magnetism and we haven't even touched on alternating current yet. There's a reason for that. Electricity and magnetism are incredibly closely related, and the two are very dependent on each other. So before I can get further in stuff with electricity, we need to talk about magnets. Now, before I get started, and yep, there was a mistake on the next slide. This is the last chapter on your first exam. Your first exam is going to be Friday, October 2nd. It's going to happen during this time period. So it goes online at 3 o'clock, and it has to be uploaded by 4:05. I'll be on Zoom in the meanwhile. It'll be 4 problems, one from each chapter. So the first problem will be something, and I'll talk about this more when we get to the end, but the first problem will be something with Coulomb's law or electric fields. The second one will be either something with capacitors in parallel and series, or something with potential energy and potential, or maybe some mixture. The third one will be a Kirchhoff loop, and the fourth one will involve magnets. As I said, I'll write this out explicitly at the end of this chapter. This next slide has a very small mistake that I'm going to fix real fast. So what I'm going to do is I posted it says last semester, is actually last year. This class doesn't happen every year. I post last year's exam. So if you go into Vanco Hall, it should really make it so it looks like what you guys looks like for you guys. There will be a section for the exam for this year. That's where you'll find it. But beneath it, you'll find the fall 2019 exam one. This is not only, as I said, last year's exam, but this is in the format it's going to be in. This file here is not going to be graded. You can do what you will with it. But what you'll go is you'll find there'll be 4 problems. And this is what it's going to look like for you. It's going to be in Vanco Hall. Numbers are going to be kind of randomized. And you'll do the work on a piece of paper, take a picture, and upload it. One page for each problem. So feel free to look at this, see if you know what you're doing, and so on. I will go over the solutions to last year's exam. I would do that on the 28th. And then the 30th will be bonus review. If you cannot make the exam time, because they're only going to be open, sorry, I just saw the question in the chat. The old exam is not for a grade. I am not grading the old exam. I just put it there for practice. And I put it in the same format just so you could see the format. Yeah. I am going to go over the solutions to last semester's exam on Monday of next week. Wednesday of next week will be extra review. Oh, if you can't make it to the actual exam, because it's only going to be open from 3 to 4:05, you need to let me know sooner than later. Please let me know as soon as you can. I will make sure we'll work stuff out if we need to. But if you miss the exam and you don't contact me, you're getting a 0 on the exam, which is going to probably screw you over. So, any questions from the one person in the room? Any questions about the exam before I get into the stuff? Okay, so magnets. That's what we're talking about. They are incredibly useful. Most insects actually use magnets in the magnetic field of Earth to navigate. It is how speakers work. Well, at least I think they still work this way. It's how they always work. They work through magnets. It's how an old school hard drive works. It's how a credit card strip, which I guess I don't use much anymore, how they work. It's how a lot of these things we don't use much anymore, I guess. But like tape, as in video and audio tape, that was them. It's how a motor works. It's how a bullet train works. It's anti-lock brakes. It's everything. So we should actually talk about what the hell it is. That is true. So here's the idea. Moving picture out of the way. Natural magnets, which are originally called lodestones, were actually found 6th century BCE. They were found in a place called Magnesia, hence the name. And the general idea is they're like, if we take this thing and we take this thing, they pull themselves together. And that this guy, closer, will pull himself to the other one. So obviously there's supernatural forces at play. The gods are pulling these things together because they want it to be, and that's what's going on here. Um, Around 4th century BCE, the Chinese people learned how to make magnets, and they learned that if they had something magnetic, they could create something else magnetic by putting them together in certain ways. They developed the first compass, and people were like, "Look, they stick together," but that was all they knew. No one understood how they work, which I always want to really quote a bad song right here, but no one understood exactly how the magnets worked for a long time. But let's get into what they do before I get into how. Here's the general idea. Magnets have a north and south pole. They're so-called, okay, I'm going to do a quick aside before I get into this. I said before how like Benjamin Franklin named things wrong. Like if he had said electrons were positive and protons were negative, everything would be much easier. We're going to be dealing with that again. People made a naming convention before they understood what was going on, and it could have caused some issues, but we'll get there. But the general idea is that magnets were named because if you take a ball magnet, one end would always point north, one end would always point south. And so they called the end that points north the north pole of a magnet, and the end that points south the south pole of a magnet. And all magnets have a north and south pole. These are kind of small. I might switch to a video. But if I try to push the same pole of a magnet together, and if I put these two magnets together that don't want to be, this guy's going to come shooting off. That's because those two poles didn't want to go together. Yeah, let me switch to video. If I bring the north pole of a magnet near a north pole of a magnet, or the south pole near a south pole, they're going to push each other away from each other. But if I put the north towards the south, it sucks right on. And so right now, it's pushing away. But when I had flipped it, right up. Here's the problem with this. That means the north pole of a magnet points to the north pole of the world, but north is attracted to south. So if you actually view the earth as a magnet, the north, what we call the north pole is the south pole of a magnet, and vice versa, because they said north points north. But logically it doesn't. The north would always go towards the south. It's annoying. But in general, all magnets have these poles, a north pole and a south pole. And north pulls towards north, north and south attract, north and north repel, south and south repel. Just like when we were dealing with charge, we had electric fields. With magnets, we have magnetic fields. Magnetic fields are represented with the letter B. They are a vector. I do not know why they're B off the top of my head. And they are measured in the unit of Tesla. We mentioned Tesla, Nikola Tesla, a little bit. Last chapter, was that last chapter? We're going to talk about him more as we go because he did a lot of stuff with magnets, creating the first AC motor. But yeah, units of Tesla. Sometimes people use the units of Gauss. Well, 1 Tesla is 10 to the 4th Gauss. This is because a Tesla is a very strong magnetic field. When I used to do research, we had a 7 Tesla magnetic field, and that is strong enough that if you were actually in the field, it would be lethal. Like, they're very strong. In general, magnetic fields run north to south, and they look a lot like electric fields if you had 2-point charges. And in fact, if you take just iron shavings and put a magnet in, and here we go, putting a magnet into that, you'll find that the iron shavings will line up and match the magnetic field. Once again, moving from North Pole to South Pole, giving a nice little, there you go. And that's a magnetic field. That's the B field. It's sometimes called B field because it's represented with B. So if you hear me say B field, that's why. And so yeah, that's the there you go. And that's what it is. That's why The magnetic field would always be, if you put a compass there, which way the compass would point. And that is how compasses on Earth work. Earth has a magnetic field around it. Could be seen with the iron filings in a magnet, like my video. Of note that if you just have a regular ball magnet, as I said, it looks exactly the same as an electric dipole, where an electric dipole is going to have a positive charge and a negative charge and the electric field between them. And in fact, if you instead take a horseshoe magnet, like my picture in the bottom right, that has kind of tilted in sides, and I apologize, I have a really nice one like this in real life that you would normally see, but I didn't bring it home because it's heavy as hell. And I didn't take a video of it because it's kind of like, look, there's a thing. You'll find that it'll have a magnetic field inside the plates that looks a lot like the electric field between parallel plates. And so the magnetic field follows a lot of similarities in how it works with electric field. Now, similar to charges, where like light charges repel, unlike charges attract, these magnets work the same, as I already said. But here's the weird thing about magnets. Magnets are a permanent dipole. If you have a ball magnet, one side's north, one side's south. If you break it in half, you get a north and a south and a north and a south. You break that in half, you get 4 north, 4 souths. A magnet can never exist with only one pole. All magnets always have a north pole and a south pole. And even if no matter how much, because these are going together here, I can try to split this however I want. You'll always have, one north pole and one south pole. You can't get away from that. Okay. Now, why that is, why you always need a north and a south pole, that gets into the magnets. How do they work? So, this is going to get slightly ahead of myself, but magnets normally come in 2 flavors, permanent magnets and non-permanent magnets. Think about the fact that if I put this magnet, nope, that didn't work. Okay, my pen is attracted to this magnet. That's because my pen is acting as if it's a magnet. But if I move my pen towards another pen, they don't go together. Basically, things that are attracted to a magnet, but not attracted to other pieces of metal, those aren't permanent magnets. Permanent magnets are ones that always are magnetic. A permanent magnet, what happens is they're caused by electron spin. Now, this gets really confusing and very hand-wavy, and kind of on purpose hand-wavy, but when you look at the quantum numbers of electrons, which we're going to cover at the very end of this class, but for every electron, we talk about its spin. And what we say is that if you have an electron, and if we pretend the electron's a little ball of metal, it could either spin one way or it could spin the other way, clockwise or counterclockwise. Fun fact, that's not at all true. Electrons cannot be treated like little balls of metal. They also don't spin clockwise or counterclockwise. But here's the cool thing. If you pretend they're little balls of metal and you pretend they spin, the math works. So physicists literally do that. They acknowledge this isn't true, but we're going to pretend it's true because it makes the math work. But if you do that and make that pretend, and everything works perfectly if you pretend, what you say is that the process of these electrons spinning causes the magnetic fields. You see that as these charged particles, because that's what an electron is a charged particle, is as it spins, the process of it moving is causing a moving charge, aka a moving charge, a current, or a moving electric field. And we'll get into how those relate to magnetic fields again in a second. But the process of them spinning is going to cause this magnetic dipole. And that every time an electron is spinning, it forms a north and south pole along its axis of rotation. Now, in a random piece of metal, in all the things I grabbed, I did not grab a random piece of metal. Okay, slinky. In this slinky, all of the electrons are all spinning one way or the other. It's only called spin up or spin down, but they're spinning in all different directions, but they're random. They're just doing whatever and all pointing in each direction, like my picture in the bottom center. And what it is magnetic fields are vector. So you might have one pointing this way. Well, let's do my arrows. You might have one pointing this way, but you might have another one pointing this way, and they'll cancel each other out. And since they're all just randomly, the random chaos of every vector will balance out to just be nothing. Because for everyone going this way, if it's random, there's probably one going the opposite. And they'll all just cancel each other out. What happens though is sometimes you can make them line up. And if you get them to line up so that they're all pointing in the same direction, all the spins, if they're all the spins are in the same direction, you get a magnetic field. Because since they're all going this way, and if every single electron goes this way, it all goes that way, it forms this field. And that's what a permanent magnet is. It's something that all of the electrons are aligned and all spinning the same way. Now, once again, they're not really spinning. It's a lot more complicated. Whether or not an electron is matter or a wave is even more complicated. We will cover that later on. And in fact, you can explain how electrons work in the real world with teaching them as waves with quantum physics. We'll touch that again later on. You can really explain what's really happening. But even with the real explanation of what's happening, we still call it electron spin. My research was actually in spintronics. Like that is what my PhD is in, is spintronics, because it's studying electron spin. Even though electrons aren't spinning, even I have a PhD in pretending they are. It's the way it's always treated. But anything that is highly magnetic, what it means is that the electrons' spins can line up. And certain metals like iron, nickel, cobalt, we call them ferromagnetic. And ferromagnetic materials are just something that it's called the magnetic domains, but basically it's a fun way of saying all the electron spins, that the electron spins line up. And if the electron spins line up, you say the magnetic domains line up. And you get a magnetic object. Now, I already said before, magnets kind of come in two flavors. The things that are always magnetic, and the things that are only magnetic next to a magnetic field. Like the front of your refrigerator is not a magnet until you put a magnet on it and then it sticks. I want to make sure I don't have another video for this, because I might. Nope. We call those hard and soft magnets. And here's the idea. Something is magnetic when all the electrons are lined up. A hard magnet is something that is hard to move the electrons. A soft magnet is something that is easy to move the electrons. A soft magnet doesn't mean it's soft. This slinky is a soft magnet. It doesn't mean it's like a soft metal, although it is kind of soft. Nope. There we go. This random Tetris block, because that's a thing on my desk. This is a soft magnet. It's not actually magnetic, but it is in the presence of a magnet. It doesn't mean it's soft. What hard and soft magnet means is hard magnets are ones that once the domain is put in a place, it's going to stay there. And what that means is with a hard magnet or a permanent magnet is if you line up the domains and you get all the domains, all the spins in the same direction, it'll stay like that. And that's going to be your permanent magnets, like this guy I keep playing with. Because this guy it's a magnet, it's always a magnet. I can demagnetize if I put a lot of effort, but it won't be easy. That once it's magnetic, it stays magnetic because the domains don't want to move. A soft magnet is something that domains can move freely. This is a soft magnet, or this Tetris block. Let's go back to that. This is a soft magnet. The reason why is that the domains are right now randomized. But if I move a magnet towards it, what's going to happen is, let's say I have the north end of this magnet on the closer side. If the north end of this magnet comes closer, it's going to pull the south ends of all the dipoles in this guy pointing one way and push all the north ends the other way. And so it's going to become magnetic because by being in a magnetic field, being near a magnet, it's going to cause all of its electrons to go from random to lining up with the magnetic field, becoming a magnet, causing the attraction. That is what a soft magnet is. A soft magnet is something that is magnetic, is not a magnet normally, but is one in the presence of a magnetic field. This is a lot like the static electricity from chapter 20, like the balloon, how I charged the balloon and put it up against the wall and it stayed up against the wall even though the wall wasn't charged because the charges move inside. It's the same idea. And so anything metal that magnets stick to, but is not magnet on their own, is a soft magnet. And just because in the presence of a magnetic field, the electrons line up. Okay. Now, the biggest magnet that we deal with is the Earth. The Earth is just a huge magnet. It's why, like I said, a lot of animals use it. It is why we have the Aurora Borealis and the Aurora Australis. Why the Earth is a magnet? There's the traditional reason people think it's a magnet, but then there's the more complicated reasons that are more likely. But the simple way to view it, which take this with a grain of salt because not everyone believes this anymore, some do, some don't, is that the because the core of the Earth is solid and metal and is spinning, that is just like us spinning electrons, it's a spinning ball of metal that creates a magnetic field. And so what happens is the spinning molten metals of the Earth's core is going to cause a magnetic field. And Earth just looks like a big ball magnet. Now, that, as I said, the thing is kind of messed up with naming, though. We name a north magnet as the thing that points north, but a north magnet is attracted to south. So the northern pole of the planet is a south pole of a magnet. And if that's not confusing enough, we've messed it up even more. Because the north pole of a magnet, the north pole of the planet, geographic north pole, like where Santa lives, is, if it was a magnet, the South Pole. That being said, though, they don't happen at the same spot. You see, the Earth, as it spins on its axes, has a very set top and bottom that it rotates around. However, the spot it rotates around is not the exact same spot as what a compass points to. The compasses actually are about 1,000 kilometers, what it views as magnetic north versus geographic north. So here's my very confusing sentence. The top of the planet is the geographic North Pole. About 1,000 kilometers away is the magnetic North Pole, which is the South Pole of a magnet. Because even though it's the South Pole of a magnet, we still call it magnetic north because we suck as a society. Yeah, there you go. So geographic North Pole is the very top. Magnetic north is a little close, and magnetic north is really south, and vice versa for the bottom. That picture is probably the best description you're going to get of that. Questions? I hate that stuff. So what can we do with magnets besides just boop? Well, let's think about this. If the magnets are due to electrons spinning in circles, we're going to keep pretending that. And literally, as far as you get in physics, no matter how high you get, even studying electron spin, you keep pretending it's electrons spinning in circles. If it's moving electrons, that means logically that magnets should affect moving electrons. And they do. Anytime you have a magnetic field, magnetic fields will apply force to moving charged particles. Now, if you have a magnetic field and you just put a charged particle in the middle and it's stationary, doesn't care. But if the charged particle is moving, it will feel a force. And the force on the charged particle will be QVB sine theta. Q is the charge of the particle, V is the velocity of the particle, B is the magnetic field, and theta is the angle between B and V. Now, I'm going to be honest. I am mildly glossing over this equation because really, what this equation is, oops, sorry, did not mean to do that, is that the equation is F equals QV cross B. It's a vector algebra with a cross product. If you take this a calc-based version of this class, you're going to have to deal with cross products. But for now, I assume most of you don't even know what a cross product is. We're not going to worry about it. And say the magnitude of the force is QVB sine theta. Well, once again, theta is the angle between B and V. This force is called the Lorentz force. And as I said, it's any time you have a charged particle in a magnetic field. So before I show this in action, because I'm going to, let's explain how this works. Let's say I have this uniform magnetic field, just pushing to the right. Just, there you go. And I put a charged particle in it. If that charged particle is stationary, it feels no force because its velocity is zero. If it's stationary, it has no velocity, it doesn't move. Let's say this charged particle moves parallel to B. Well, if it moves parallel to B, that means the angle is 0 degrees. And the sine of 0 degrees is 0. So if it moves in the same direction as the magnetic field, it also feels no force. But let's say instead it moves perpendicular to the magnetic field. If it moves perpendicular to the magnetic field, now we have an angle of 90 degrees. The sine of 90 is 1. Now we got a force. We have a force of QVB. Now it feels a force. And it ends up that a charged particle only feels a force in a magnetic field if it's moving and not moving in the same direction as B. But also, force is a vector. We need to know what direction it is. And I could, if we knew this cross product thing, get the direction that way. But if we don't know that, we need another way to get the cross product. And now I'd like to introduce the first of many times I'm going to use the phrase right-hand rule. The right-hand rule is a way to approach, in general, anything with a cross product in it. But is a way to approach what direction this force will be. And almost everything in the next 3 chapters, when I ask for direction, the answer to how to find the direction is to take out your right hand and move it around into weird spots. It's going to be a lot of that. And here's the idea. For a moving charge in a magnetic field, if you want to find the direction of the force, point your fingers, take your right hand. You got to use your right hand. Take your fingers and point them in the direction of V. In this case, V is up, so I take my hand and point it up. You then curl your fingers and make it so after you curl your fingers, your fingertips point in the direction of B, which I got to be careful here because I think I mirrored. So this curling to match B on the screen should be like that, if I'm not mistaken, which for me looks backwards. And so when I curl my fingers in the direction of B, my thumb is pointing right at my face. Wait. Yeah, but I'm doing it backwards. That's the thing. I'm doing it backwards because it's mirrored. So if I match this, it's going to point into the page. And even though for you this probably looks backwards, trust me, that's into the page for me. And so I'll take my fingers, point them towards V, curl them to B, and wherever my thumb points, that's the direction of force. And you can try this. Put your hand in the direction of V, curl your fingers to match B, and look, your thumb is into the page. That's the force. The force is into the page. One thing to note, really though, your fingers shouldn't be in the direction of V. They should be in the direction of QV. Oh. Yeah, I'll do that. So if Q is ever negative, swap it. If Q is negative, say, hey, negative times V, that switches the direction. And so instead of putting your hands in the direction of V, if Q is negative, turn it 180. And this will always give you the direction of the force. Now, this force will always be perpendicular to V and perpendicular to B. We're going to go 3-dimensional on this shit, but it will always be perpendicular to both, even if V and B are not perpendicular from each other. Force will be perpendicular. If my charged particle is up at an angle theta, as drawn here, this new one that showed up right here, if I want to know what direction, I'd say V is up at an angle. I'd curl my fingers towards B. Thumb is the force. It is into the page again. So to show you this, what I have here is a cathode ray. Cathode ray, what it really is a bunch of electrons moving in a line through something that makes them glow. And so this green line is literally just electrons moving rapidly to the side. And so the electrons are moving right now to the right. When I take a magnet and approach, when I bring a magnet near the end, they curl up and down, depending if it's north or south. I'm adding a B field either into or out of the screen, depending if I was using the north or the south. V, B. Okay, yeah. I'm doing either into or out of the screen, depending north or south. But even though I'm adding a magnetic field into and out of the screen, it's bending up and down, perpendicular, because they will always bend perpendicular. Now, that being said, to solve this, we're going to have to draw a lot of three-dimensional vectors. We're used to drawing vectors just on a flat thing, right? Is it pointing in X? Is it pointing in Y? Is it pointing in Y? That's it. You're going to see this notation a lot moving forward, either a circle with a dot or a circle with an X. That's to represent into and out of the page. And the idea is you treat it like an arrow. A circle with a dot is you're looking at the front of an arrow, and it's the point at you. That's what the dot is. Anytime you see that, that means it's coming out of the page. A circle with an X is supposed to be the feathers on the back of an arrow. Like we're literally talking about like a legit arrow, like bow and arrow, you're shooting something at someone. And the X is the feathers on the back of an arrow. So if you see an X, that is into the page. Questions before I do an example? Okay. So let's do an example. Here we go. An electron is moving in a direction perpendicular to a uniform magnetic field at a speed of 1.5 times 10 to the 7th meters per second, and it's undergoing an acceleration of 4 times 10 to the 16th meters per second squared to the positive x direction, when the velocity is upward, positive y. Magnitude and direction of the magnetic field. So I'm going to draw this. So I'm saying this thing is accelerating to the right, and we know F equals ma. So if it's accelerating to the right, that's the direction of F. And it has a force that way when it moves up. Okay, so I can right-hand rule this, but backwards. See, I said to put your hands in the direction of V and curl your fingers towards B. Your thumb is F. Now, I obviously can't really curl my fingers in the direction of B if I don't know where B is, but I can explain it. I can say V, I need my thumb to point towards F, and go and say, oh, okay, that's out of the page. But wait, because V, F is, because V's up, thumb is F, there you go. But that's not right, because I said an electron. Electrons are negative. And so I shouldn't say V is up. I should say I should pretend V's down. And I have to tone my entire body, and gonna have to stand up for this. So V's down. My F I want to be to the right, which once again, I feel like I'm going to see if I can make this stop mirroring me so that you see me as backwards as I see it. Because what's happening is the, oops. What happens is it mirrors my video, which throws it off. Oh, that's great. It mirrors it again. So now I see it backwards. That's confused myself a lot. So I'm going to say it's down. It's in that direction. And so I'm going to say, sorry, thumb. It's down. My F is, and I have to tone this in, and that's into the page because it's negative. Okay. Once again, with video, this is hard because it's mirroring. Just play with your hands on your own, whatever that means. And I'm sure you will see what I mean. So That's the direction of the magnetic field. It's into the page. Now I can get the magnitude. If I want to get the magnitude, F equals QVB sine theta. But F is also MA because F is also always MA. So as long as I know the mass of an electron, which I'd give you if you need to know, and I gave A, I could say, and I know V, I could say F is MA is QVB sine theta. But they were 90 degrees apart. And the sine of 90 is 1. So the magnetic field is MA over QV. With by plugging in a few numbers, I can get a value. I'm sorry, this right hand, like, basically I have a little image of myself that I'm using, but I know how I see and what you see is reversed. So when I say something's to the right, it's probably to the left to you, and that's just going to be weird. So you're going to just have to, as I'm talking, move your hands around. Side note, it's a lot of fun to watch people do Physics 2 exams, because as you guys are doing exams, when I walk around, I just see a lot of people doing this the entire time, because that's how you do these. Okay. So let's say you do this. You take a magnetic field, you throw something in. When you have a force perpendicular to B and V, when it's perpendicular to both, what that's going to mean is that the magnetic field does no work. It does no work because if the movement and the force is perpendicular, that's going to be no work. And what that happens is anytime you put a charged particle in a magnetic field, it's going to move in a circle if left to its own. Like a satellite. Because if I, in this setup, if this is a positive charged particle and have set its velocity going straight up when it enters this magnetic field, if B is into the page, my thumb points to the left, that force to the left is going to turn it. And this is going to be just like dealing with centripetal acceleration. And since it is centripetal acceleration, so it's just like it because it is that thing from physics 1. We'll say F equals ma, but it's moving in a circle, so A is V squared over O. Now, if these two fields are perpendicular, that means it's going to be QVB sine theta, which is QVB, equals mv squared over O. I can divide both sides by V, and with a little bit of rearranging, get this equation. It's called the cyclotron equation. And what it is anytime you have a moving charge in a magnetic field, as long as V and B are perpendicular, it's going to make a circle. And the radius of that circle will be the mass of the the mass of the charge times the velocity of the charge times the charge of the charge, divided by the charge of the charge and the magnetic field. You have a lab coming up. It's not the one due this week, but the one due next week is actually going to be doing this. You're going to be looking at a charged particle in a magnetic field, and it's going to go and make circles. It's what this does. And actually, depending on which way it goes, you can find the sign of the charge. And actually, let's think about this. Depending on what it is, well, that's our sign of the charge, right? If you have a charged particle, you want to know if it's positive or negative, set it moving in a known magnetic field. If I have a magnetic field into the page, the force has to always point to the middle of the circle. So for that first one, I'd say its velocity is this way. B is in. My thumb points to the center. The top one must be a positive charge. The top one must be a positive. Sorry, I got ahead of myself. My forces have to point to the middle. And following it, the top one has to be positive because V, B, it works. But the second one, V, B, my thumb pointed up and the force pointed down. That means it breaks the right-hand rule. That means if V was the other way, it would have worked. That means it must be a negatively charged particle. And this is actually used like this. There is something called mass spectroscopy. that mass spectroscopy is a fun way of basically saying, we got this charged particle. What's its mass? What's its charge? And using this, we can solve for exactly what is its mass and what is its charge. And what you do is you take the particle and you shoot it into a region of magnetic field. And you see how much it bends, what its radius is. By seeing what its radius is, you take this detector and move it left and right. And seeing where the detector is hit, you can say, okay, now that I know the radius, I can get the mass charge ratio. And that's actually what you can solve for. Using this, you cannot solve for the mass of a particle. You cannot solve for the charge of a particle, but you can get the mass charge ratio. And that's actually the more important thing normally anyways. But just by measuring the radius, you can always get that ratio. Okay? Okay. Let's do an example problem. And this will probably be our last one for the day. So, I got this thing with two chambers. Each chamber has its own magnetic field. A positively charged particle enters chamber 1 with a velocity of 75 meters per second and follows the dash trajectory. The magnetic field in the region is 1 Tesla. The radius of the dashed line of that region is 0.2 meters. So, what's the magnetic field direction in both regions? What's the mass of the particle? And given the second radius, what's the second magnetic field? So let's start with direction. V, I just did a point. I'm just going to do a point right here. And at that spot, V is in that direction. Using the logic of centripetal acceleration, the force has to be pointing radially inward. And I said it was positive. So V, and whatever direction I curl my fingers, my thumb needs to point at F. And so, okay, my thumb needs to point at F. That's like this. And so B must be out of the page. It's out of the page because if I do into the page, F is pointing up instead of down. And so there you go. Once again, you might be seeing me move backwards versus the figure. Just do it yourself. Because I'm going to be mirrored. Do it yourself and it'll match. Now, V2, it's now going in the other direction. The force is now up that way. And so V, I want F to be move like this. V's up like this. I want F to go that way. Well, that works. I don't have to contort my body this time. That has to be into the page. So now that I got my directions, what's the mass? Well, in region 1, I got the velocity, I got the field, I got the radius, I got the Q. Find M. I can just use this equation. I'll multiply both sides by QB, divide both sides by V, and by plugging in some values, can find the mass. In region 2, if everything's perpendicular, the velocity is not going to change. The charge isn't going to change. So I just have a new radius, get the new B. So I say, okay, here's my equation. I want to get B, multiply both sides by QB, divide by all Q, plug in, and there you go. Questions to the one person? I like to keep thinking that people are actually watching these videos on YouTube, except my YouTube show views proves that no one is. So I'm just going to be depressed. .5 minutes. So I'm thinking about how much further I want to go here. I think that's probably a good place to stop. It's 5 minutes early, but I'm about to start a whole nother thing, and I hate to start things and stop them. And I'm pretty sure I have enough time to finish what's left. So I'm going to stop there, a few minutes early, and just say that way I don't stop in the middle of a topic. So once again, exam is October 2nd. Charged particles and magnetic fields, they spin in circles. That's the summary. Don't forget homework Wednesday, and have a good day.